Navigating rough ground requires physical force. Most animals push with legs, pull with arms, or generate lift with wings. Yet the snake moves rapidly across the earth at high speed, entirely without arms, legs, or wings. When you watch this fluid motion, it appears as though the animal is simply sliding over the dirt or being dragged forward like a length of rope. This diagram outlines the physics problem. Conventional locomotion relies on traditional leverage, an appendage pushing against a solid surface to transfer energy. A flat tube lying on the ground lacks a pivot point, which makes generating forward momentum a mechanical challenge. The propulsion actually comes from a system hidden beneath the skin. A snake's body houses hundreds of individual ribs, each connected to a sequenced network of muscles. To understand how this works, we have to look at how these hundreds of individual bones and muscles fire in coordination to drive the body forward without a single external limb. This motion relies on a specialized internal skeleton that allows the animal to interact with the ground in a way that wheels or legs cannot. This X-ray schematic shows a flexible spine connected to 400 pairs of ribs. Muscles contract in a timed sequence, creating a kinematic wave. For friction, belly scales interlock with the earth exactly as the wave passes. This system is known as serpentine locomotion. The internal wave pulls the rib cage into a continuous lateral S-shape. As the curves of that S-shape press against rocks or twigs, they create temporary pivot points. The snake uses these points to convert lateral muscle energy into forward momentum. The animal does not slide. It propagates energy through a flexible skeletal frame to actively push its body against the environment. While serpentine motion works on textured surfaces, the snake must adapt this kinematic wave when it encounters loose sand or narrow crevices. In loose sand, snakes use sidewinding. They coordinate their muscles to lift sections of their skeletal frame into the air, maintaining only 2 distinct contact points with the ground at any time. This reduces surface area contact, which prevents the snake from slipping in the loose grains and minimizes contact with the hot desert floor. In narrow spaces, the wave shifts into concertina movement. The snake anchors itself against the walls with its rear ribs, allowing the front half of the body to stretch forward like an accordion. Heavy species, such as pythons, utilize a different mechanical sequence known as rectilinear movement. Instead of moving side to side, the snake lifts specific sections of its belly scales, stretches them forward, and pulls its frame in a straight line. The snake modulates its internal engine by adjusting the amplitude and frequency of its muscle waves to navigate almost any surface. This coordination is highly efficient. Using these kinematic sequences, a black mamba can travel across the ground at speeds up to 20 kilometers per hour. Engineers are now reverse engineering this muscle-to-bone sequencing. They are mapping out pathways for segmented robotics that can replicate these biological movements using servomotors. These machines are designed for irregular terrains, such as disaster zones or cave systems, where wheels and traditional mechanical legs often fail. While we can build complex processors, human engineering still lacks the fluid efficiency found in the biological original. This mechanical coordination evolved over millions of years. Once we can replicate it, these machines will access